Okay.
Yeah.
Can you see my screen and my voice is clear?
Yeah, it's clear. It's clear.
Okay.
Go ahead, please.
Thank you, Chair, for your presentation. And thank you also to colleagues, Professor Amish, the Chairman, for inviting me to this interesting conference. And I apologize for attending just online, but we tried to cancel for unknown reason. Anyway, we are very close. I am here and you are there. This is an overview of my university, the University of Salerno, started 40 years old. We count for 70 different faculties. Thanks to the working group and some collaboration that I have had during these years with Professor Razza Kapoor from Canada, Frederick Carbon, a friend of mine, with you in the moment, Saverio Sparea from University of Bari, in south of Italy, Marco Lamberto, Luigi Granata, my previous PhD students, and also two colleagues from Naples, Mario Daniello and Liberata Guadagno. And also thanks to industries, Fiberland in Denmark, and Topoglass and Mascherpa in the north of Italy for having support my research during this year. This is the outline of my presentation. First of all, we speak about FRP, and my research lives in the field of civil engineering. We can speak about the open problem of connection with a particular regard to beam-to-column connection, studying the aspect of durability and ductility. For us, in civil engineering, an FRP material is a combination of two materials, resin and fibers. Among fibers, the most used one is the glass fibers, because it's the cheapest kind of fibers that we have on the market. The final product that is obtained by pultrusion process, which is here briefly described, is a mix. As you can see here, we have fibers, glass fibers, embedded inside resin, and this mix, sorry, I want to go fast, and this mix come inside a mold for the final shape of this kind of material, which shape is something like this, mimicking the steel profile. The mechanical properties of this final product is something which is characterized by an high corrosion resistance, an high ratio strength weight, an high ratio stiffness weight, and linear elastic behavior up to failure. Among the first and the last features of this material we can discuss in the next. First of all, the behavior of an FRP materials is an intermediate between that of resin and fibers. And if we can make a comparison between glass with respect to, for example, steel and aluminum, which are two natural and main use material for construction, we can say that in terms of strength, in particular axial strength, the value of glass are 4 times bigger than that of steel, for example, and also the density of this composite material is 4 times lower than steel, for example. So this means that we can have very strong structures and very light structures at the same time. Actually, we have an Eurocode since 2022. It's called Design of Fiber Polymer Composite Structures, and this Eurocode is a combination of several guidelines available in several countries of Europe. for example, this one was the Italian document by Council National Research in 2007, and I have the fortune to take part in both writing of both codes, the Italian one and the European one. In both Eurocode, the connection technology allowed and mostly adopted is the bolted one. This, thanks to steel structure experience, use steel structure experience moved to the composite structures because of these structures mimics steel structures, and also the presence of steel parts in terms of bolts and plates guarantee ductility. On the contrary, the interruption of the fiber continuity, because as you can say, a fiber composite material is made of unidirectional fibers, this one, covered by a veil or a stole in order to protect the fibers from the environmental agents. Obviously, if we can make an hole, holes inside these structures, this is a point of for these kind of structures. So, in order to bypass, to overcome this problem, a possibility is to adopt the adhesive technology, similar to exactly the same technology Frederick have presented, or a combination of them, adhesive and bolted. First of all, why it is useful to speak about an adhesive connection from a technological point of view? If we can try to make the same experimental test on the same beam to column joint, we have the same, the column is a square and the beam is a built-up beam. The static test was performed applying a vertical load at the free end of the beam, and if we make a comparison, the blue curve is adhesive and the orange curve is for bolted connection. It's possible to see that we have the strength, the stiffness higher adhesive with respect to bolt, and just point in favor of bolted connection is the failure mode, because of the failure mode for steel is B. The failure mode of composite is brittle due to the elastic behavior up to failure. Obviously, for an earthquake reason, an earthquake needs this kind of failure for composite material is not. We have to also to overcome these difficulties. The final shape, built up beam and a box set for a column, was selected after a previous in 2017. We try to connect by adhesive, obviously, two open profile. In this case, the adhesive is this one, and the failure inside the adhesive is in mode 1, is an opening mode. This means that when we move from this technology, from this shape to this one, obviously this one is available for two reasons. First, we have two adhesive layers instead of ones, and the failure is always inside the adhesive, but now adhesive works in mode 2 of failures and not in mode 1. If we make the same experimental test applying a load at the free end of the beam, and we show the results in terms of moment versus rotation, it is possible to say that we have a generally linear elastic behavior, while the failure is cohesive inside the adhesive. So once we have decided that it is feasible to speak about adhesive connection, we have to discuss about the problem of durability and ductility. First of all, we have studied durability. The first step was to create the mechanical properties of two different types of resin
immersed in seawater and tap water at the temperature of 2 degrees for a period of 15 minutes. The curing temperature of the curing temperature, ambient temperature, was selected to simulate as much as possible the real employment in civil engineering. The maximum temperature of 30 degrees was selected for two reasons. In the specific case of seawater, it represents the most severe environmental condition, while for both conditions it accelerates the diffusion and promotes the degradation. So we discuss about Cicador and Araldite in details. About the differential scanning calorimetry tests, we evaluated both glass transition temperature and also the curing degree of both resins. And in particular, we selected 45 degrees for Cicador 30 and 70 degrees for Araldite for what we call the glass transition temperature, and 82% of curing degree for Cicador 30 and 90% of curing degree for Araldite when the curing temperature is the ambient one, more or less 23 degrees. If we check about absorption behavior of Araldite and Cicador 30 in seawater and tap water, we can say that more or less the quantity of the absorption into the Araldite resin is 4 times bigger than that in the adhesive. After that, the second step was evaluation of mechanical properties not only of resins but of resins used for connecting two GFR adherents, two glass fiber reinforced adherents. Obviously, the curing and immersion conditions are exactly the same adopted for the resin. We conducted a very wide experimental test, more than 162 end-notch failure test. The shape of the cement was this one. The thickness of the resin was 1 millimeter. Here there is an original wax in order to facilitate fracture propagation. If we check what happened in terms of absorption behavior, moving from seawater left to tap water on the right, it's possible to see a completely different behavior. In the sense that in order to achieve the final water intake in seawater, it needs 4 or 5 months with respect to tap water. Why this phenomenon? In some cases, authors attribute this phenomenon to the presence of salt in ecosystem, resulting in a lower equilibrium by virtue of its lower chemical activity. Another possibility is that salt that cover the surfaces of GFP adherents obstruct the water permeation through the. In general, we can say that in order to reach final intake in tap water, we need a month. In order to reach final intake for seawater, we need 5 months. More further, if we want to evaluate the mechanical behavior of resin after absorption behavior, we performed the notch failure test, which schematic view is top on the right, in which we have a simply supported beam and the load is applied at the central section. The results are expressed in terms of forces versus displacement, and the displacement was recorded at the same cross section where the load was applied. On the left, we have results for Cicador 30, the Araldite resin, after absorption, after aging in seawater and tap water. What we can say is a completely different behavior as in the past. In fact, in the case of Cicador 30, in terms of stiffness, in terms of strength, nothing changed after absorption in terms of seawater and in terms of tap water with respect to an aged specimen is more or less behavior is the same. A great difference is for araldite when moving from the unaged specimen to the seawater aging, tap water aging. Now, why in the case of Sicadur 30 nothing happened? First of all, because the curing degree of Sicadur 30 was 87%. We have also another 13%. Temperature of the water 30 degrees greater than curing temperature 20 degrees activated a post-curing phase. The beneficial influence of curing is greater than due to plasticization and or hydrolysis. For the case of araldite, the decrease of araldite was due to the fact that its curing degree was equal to 98, so we have just a two further percentage. And the temperature of water differently, in the case of Sicadur 30, was not sufficient to contrast the degradation. So, what happened into the araldite? Plasticization or hydrolysis? In order to answer to this question, we tested also the specimen to the absorption, the desorption behavior. At the end of the desorption behavior, what is evaluated was the final water intake, the water trapped in the material more or less equal to 2%, and evaluating the mechanical properties as before, not only after absorption, but after absorption plus desorption. For what is possible to say that the original mechanical properties was completely recovered after desorption. What does this mean? It means that the degradation of during absorption period was probably due to plasticization more than to hydrolysis, considering the complete recovery of the mechanical properties. The final step was to test the final product, the bean-to connection. So, we did also in this case, we performed a large experimental campaign in order to test several kinds of bean-to-column connection. The results of the study are reported, as always, I reported my at the end of the slide. And in this case, what we selected for this, the connection is the same as expressed before, also was in terms of fraction energy. How it is possible to see fraction energy versus time? An initial increase of fraction energy was followed by a great increase of it, followed by a final reaching a minimum asymptotic value. This is due, again, considering that the temperature of 30 degrees greater than the cured temperature of 23 degrees. So we have a beneficial effect of post-curing. These are the results in terms of forces versus displacement or moment versus curvature of the bean-to-column. In the case unaged, water, seawater, we say that more or less, if we consider water, the mechanical properties is reduced by 15%. If we consider water, the mechanical property was reduced, mechanical properties in terms of strength and stiffness, about 20%. The rupture was completely adhesive, into the adhesive as here reported. What about ductility? Here, for example, we have one of the connection available in the literature and on it is an hybrid connection of both and these and these beams are firmly joining by adhesive together and after also bolted. we check the results in terms of moment versus curvature, we say that we have an initial linear elastic results. This elastic results is due to the presence of adhesive, which behavior obviously is linear elastic. The ductile behavior starts when plates happen inside the adhesive and the bolts started works. In order to, obviously, which is the main problem of this connection. The main problem of this connection is no repairability of the joints. In order to try to overcome these important features of repairability, we have recently designed, tested, and patented a hybrid two-column connection, and the scope and the aim of this patent try to bond the FRP elements to steel elements in order to preserve the fiber continuity. The latter steel elements are bolted to other steel components that are designed quicker than the adhesive in order to guarantee a ductile response. So our connection is composed of a nodal zone. This one in red is a steel. This red zone is connected to the column by a steel socket, and this steel socket is connected to other steel by bolts. The FRP beam is connected to this stub element by adhesive, and this steel element connected to this green element, which is the fuse, which is the element of the connection, obviously by bolts. And the green steel element is connected to the central steel by bolts. So GFRP versus steel by bolts, steel versus steel by bolts, as in this happen. Obviously, this kind of connection is if we think in order to study not only classical beam to column connection, but also we have two beams combined, or we have a beam orthogonal each other, or we have an internal load. Okay? This design, the replicability of this design is very, very simple. We perform experimental, also in this case, other experimental campaign in order to evaluate the influence on the final response by the thickness of the fuse, by the length of the stub, meaning this length corresponding also to the bonding length, to the distance of two of both. If we check, for example, some results here are load versus displacement, the kind of test is also as before shown. In this case, we have that increasing the stiffness of the steel elements, the strength increases, but the ductility increases, and making the same bolts, but considering two different lengths, 150 and 250, we have a little bit increase in terms of stiffness. If, for example, we check the results for a stiffness equal to 8 mm. If we fix the bonding length and vary the distance between both, there is also a great increase in terms of strength in these two values. If we finally is just to make a comparison between our patented connection with respect to all other connection, hybrid connection presented into the literature here. So we have a good stiffness, but we increase a lot the strength. So in order to increase the strength, we continued the experimental not into the lab by using the software is in this case. So first of all, we make an element model of what tested into the lab. We use contact formulation, friction steel, cohesive behavior, dynamic implicit analysis, for bolts. And when we comparison between what happened inside during the experimental test and what happened into the finite element analysis, we found a very, very good correlation for two reasons. All, as in the experimental test, failure is concentrated inside these three elements only. Moving from low values of the thickness to greater values of the thickness, we found a different number and position of plastic inches, from 4 to 6 plastic inches. These curves are reported in red, the experimental curve, and in black, the numerical model. The correlation was very good. In order to increase the strength of our connection, according to the comparison of other hybrid connection on the market, we tried to improve the non-zone, moving from an open section to a closed section, here reported, moved from just 2 rows of 2 bolts to a 3 rows of bolts as here reported. It is here possible to see if we make a ratio between the ultimate moment divided by the critical moment, so is bending moment, bending capacity of the. We tested. It's possible for move up to a thickness of the green element of 21 for this case and 18 for these cases. What was very, very interesting was that moving from this connection to 2 bolts, 3 bolts, low values of thickness, higher value of thickness of the screws, we have a common denominator, is the number of plastic inches equal to 3, and also the position of plastic inches, 1 year, 1 year, and 1 year. Because of the position of plastic inches now is known and it is fixed, it is possible to evaluate the strength of a connection by applying the principle of work on the formed equation. In this case, equaling the external moment m here by the rotation to the internal moment due to Φ1 and Φ2 m0, the internal moment, F stay for flanges and W stay for X, it is possible to find a solution in terms of strength, in terms of moment, in terms of ability, in terms of moment of our connection, a function of these geometrical parameters. Once strength M is calculated, we need the final was to evaluate the stiffness of the elastic. In order to do this, we selected 2 different models, Model 1 and Model 2. In Model 1, we thought about a strictly connection between green element, the fuse, and the tab. From here, in the second moment, the connection between here and here. Why is we have? Because of it depends on the load applied to each bolt divided by the preload force. If this ratio is less than 1, we have this kind of model. If this load is greater than 1, this is that we can count the contact just between the point A and B. If we try to adopt this model, making a comparison with the numerical model, which results are black, it is possible to, obviously, as expected, to see that once thickness of the steel element is very low, for example, millimeter, in this case, because of the thickness is low, m is low, and m is low, this numerator is lower than the denominator, so this ratio is than 1, and in fact, the curves closest to the empirical model curve is the red one, corresponding to model 1. Once we increase the thickness of the fuse of the element, so we increase the strength of the connection, we move from model 1 to model 2. Why? Because m is increased. Numerator could be then denominator. So we have this ratio more than 1, and in order to do correlation between numerical model and the mechanical model are by the green. In this case, a green curve is relative to the model. In conclusion, the framework to define this hybrid connection is to know the strength of adhesive, to select a partial factor in order to have a lower design value for all steel elements. All steel elements have to live in the elastic field, and only the green element have to be characterized by a plastic behavior. Because of, if we concentrate all deformation plastic hinges, in this case, element, this green element could be easily replaced by a new one. So we overcome the problem of repeatability. Thank you for your attention. I hope to be kind.